folks, so I apologize in advance for all of the chainsaw noises that you will be hearing. I will do my best to edit them out. But my apartment complex decided that today was a very, very, very important day to cut down all the trees that were dying right outside my apartment. And yeah, unfortunately, they did not know that I need to record today. Yay! Alright, so let us dive in because today we are talking about the common factor model. So recall that from classical test theory, every person has a true score. And we, in theory, in this fantasy universe, we could measure it directly without error. That would be nice. So classical test theory assumes that a person's score is comprised of their true score, T, plus some measurement error, E. And the common true score model is X equals T plus E. Now, in the common factor model, this can be essentially summarized as X sub k, where X is the number of items, is equal to T plus E, except it's probably better to think about this as variance for a second, where sigma X sub k is the product of sigma of true score plus sigma of error. Remember those variance sum laws? They're going to come into play here. So since we don't know T, we can replace it with something called common variance, or the variance that this item shares with every other item on the test. This is called commonality and is often indicated as h squared, as I've illustrated here. So instead of thinking about E as an error, I encourage you to think about it as the variance that is not shared, the variance that is unique to either that test or just measurements, the stuff that's not, that the test questions don't have in common. And this unique variance is made up of the variance that is both specific to that item plus error. And unfortunately, we can't pull those apart, because if we could, with this method, we would. But the common factor model is illustrated in this equation here. Is essentially the variance across the test is the product of the commonality, so the common variance, and each of the unique variances. So if we break this down into the individual pieces, as I've diagrammed here, the variance of an individual question is the common variance, so that's variance shared with all the other items on a questionnaire, plus the specific item variance for that specific item, plus random error. Now, like I said earlier, we can't untangle random error from specific item variance. So instead, we are left with this unique variance that is undistinguishable between those two chunks, plus the common variance. So this is the variance that's shared with all the other items. I'm looking at row 2. And kind of more succinctly, variance of an item is commonality plus uniqueness. Those are the two pieces. That's it. We can break down different pieces more and less, but that's the fundamental idea of the factor model. So the common factor model assumes that the commonalities represent variance, and that overlapping variability is due to the concept or factor that we're trying to measure, which is great. But how do we calculate these? Well, with spoilers, a factor analytic approach. Now, the easiest way, I think, to conceptualize this approach is to think about it like a factor, like a regression, where our total score, the y of our measure, is the sum of the loadings of each of the questionnaires and their specific weights. So B1 is our weight that we're putting on item 1 plus B2 plus B3, etc., plus an intercept and error variance. Now we can simplify this model and condense it to summarize the total, our y factor, the variable that the construct we're trying to measure. So we can look at it as the sum of each of the coefficients and their item. And so in this equation, we have b sub k times x sub k, where x sub k is individual item k times its beta weight, its coefficient. And then we just toss in error variance, so all the variance unexplained, as well as an intercept, just to make it nice and tidy. So we can also think about this a little more theoretically. So theoretically, items don't make up a factor, like depression. The factor should predict scores on that item. So, for example, if you know someone who is depressed, then you should be able to predict how they will respond to each question on the CESD, for example. So let's flip this model around. So instead of knowing the latent measure, the factor, because we are that total true score, which we just don't know. Instead, let's flip that so that we are predicting each question response as a function of the factor. And here, psi, that's what the trident symbol is, psi is the relationship, so the slope between the factor, so our true score, and the item, where f sub j is the factor of interest and e sub k is the error. This is the residual, predicting the item from the factor, where each k indicates a question, indicates a specific item. So notice that the arrows have changed direction here to indicate the flow of theoretical influence. So we've gone from using our items to create a measure to using our construct and having our construct predict the individual responses of the questions, and that the question responses are a consequence of that construct, as opposed to just this summation of those responses to create construct. The arrow is reversed, is what I'm trying to say here. And these two factor models, the first one is indicative of a single factor. So one factor influencing responses on all the different questions. Now the second model, the one with two circles, is a slightly more complex model, where factor 1, whatever it is, let's keep using depression as our example. So factor 1 only influences the responses on questions 1 through 3, while factor 2, let's call that anxiety, only influences the responses on questions 4, 5, and 6. There's no crosstalk, there's no dual influence. It's a very simple model. Now, the commonality that we were talking about way back a couple slides ago is a measure of how much each item is explained by the factors, and therefore is also a measure of how much each item is related to other items. And we can calculate this commonality, denoted here as h sub k squared, just as the summation of all those psi's. And just whatever is left over, whatever is not explained by this commonality, is uniqueness. So the big burning question, right? So how do we predict items with factors that we can't measure directly? And this is where math comes in. So long story short, we're going to be using a mathematical procedure to piece together almost like super variables that we are using as a fill-in, like as a proxy for the factor in order to estimate our previous formula, because we can't directly measure it, but we can use all the information we do have to almost triangulate it and give us a pretty good approximation. So how do we do it? So we can do this from a geometric decomposition. So this is an eigenvalue. For those of you who have taken matrix algebra, this should sound really, really familiar. So this eigenvalue, this eigenvector decomposition, sometimes this is called a singular value decomposition. But what it is a correlation matrix that is broken up into smaller chunks, where each chunk is a projection into a cluster of data points, or eigenvectors. And each chunk is created to explain the maximum amount of variability in the correlation matrix. And that variability is explained as the eigenvalue. And each eigenvalue is created to maximize the relationship amongst the variables, so that commonality. And each vector stands in for a factor, and that we can measure how well each item is predicted, essentially related to that factor, using the common factor model. And so that is a wrap for a very noisy introduction to the common factor model. I encourage you to go through the notes that I've written out, because those are in much more detail, and hopefully they will be helpful. The idea here is to give you a bigger conceptual overview. So I will see you later. Bye.